This video is going to focus on how I went through finding a a snake that would work for both a cube and a square, the 4x4x4 cube and the 8x8 square. And if you read the post, you know that looking at the different possible Hamiltonian paths, that's going once through each position. If I ignore rotations and reflections, then I'm looking at less than 400 million, which is far less than any of the other possibilities. So I went ahead and started with that. So you can see I numbered the squares this way, and I focused on starting with only these that you see here, these 10 options here. And I actually limited it a little more. I went with 72. You can see those here. 72 different starting paths. So what that does is kind of prevents some of the leftovers. So you can see, for example, I could go from 1 to 2, or I could go from 1 to 9, and those would be both the same thing. So I only have a 1, 2. I don't have a 1, 9. And same sort of thing. 10, 2 or 10, 9 would be the same thing. So I just have a 10, 2. Also, I took out one, like if you see 2, 10, 9, well, there'd be no way to get the 1 and get the rest of the stuff. So 2, 10, 9 doesn't show up. So this is just my way of trying to kind of limit issues of reflection and rotation. This deals with all kind of the possibilities, and then taking additional symmetries out by adding these, starting with 3 positions instead of just the 1, as in 1, 2, 3, 4, and then the rest of those. Does this eliminate all the extras? Well, certainly not in the case of ones that go backwards. So for example, if I started at 1 and somehow ended at 10, well, then when I went from 10, I would probably find the same path going from 10 backward through until it gets to 1. So I didn't eliminate all of those. And did I need to have all 72 paths going at length 3 to start out with? I don't know, probably not. But maybe you guys can look into that and see if there's a better way to kind of start the setup. Okay. So that's where I started. I basically took 1 and I'd run through, try to find all the Hamiltonian paths I can from that, and then potentially move on. I actually never ended up moving on because I found one that I needed, and I didn't go through all of the options. All right, here is the kind of initial setup. So I've got all 64 cubes, and the first few columns are the cube position. So these are the cubelets, the 64 cubelets, and their position, and so 1, 1, 1, on through that. And then these are the 3-dimensional neighbors. So columns F through K, because at most they're going to have the 6 faces, so 6 neighbors. And then we move into the square neighbors. So these are for kind of what we're actually paying attention to here, and there are 4 potential neighbors, and then it also has the X and Y position, from 1 through 8 for those. So that's how I drew the setup from that. Using the neighbors is how the path determines the possible next steps for building the path. Okay, so in some early iterations, I was trying to figure out a way to keep it as slim as possible, doing this kind of walking mechanism where it figures out what its options are, then chooses the first option and pushes on to the next spot. If it doesn't have any options, then it backs up and then evaluates the next from there. So sometimes I get in a situation where I'd have this, where clearly from here I can't get both of these at the same, so I might as well back up without even going on to the next. And you'll see some more of that style here. Clearly, once I got here, if I had skipped that, and I skipped that one, so it's a lot of wasted time kind of doing a whole bunch of different iterations through here, knowing that none of them are ever going to work because of these holes here. And that's kind of the same deal here. Have these holes, and so that's not going to work. So I needed something that would look ahead a little bit more than that. And also for this situation here, you can see it still has more options. This actually has two problems. It has this hole here, which can never be reached. And then it also has another problem that I had to deal with, which was that it has I call them a no exit. It has a no exit here. That means it can go into this, but it can't come out. And it also has a no exit here. Well, if you have two no exits, then you're not going to solve, so you might as well backtrack. So that's what we did. That's what I did. I decided to work through this situation where I created an antipath, and the antipath looks for two things. It looks for making sure that there's only one component. That means all of these blue squares are connected to each other. Anytime there's not, then I might as well backtrack because I'm not going to be able to reach them all. The other thing it does is looks for no exits. So if there are more than one no exit, then it might as well backtrack. And you can kind of see what happens as I go through. So you can watch it build. Goes through. Another thing that the option does, because I knew that I wanted these to be to fit into the cube, it never lets more than two straights happen in a row. So as you can see, if I just move back for a second. So once I'm here, it seems like a reasonable option would be to go straight ahead, but I forced the program to turn so that it, because if it went straight ahead, it clearly would never be able to fit into a 4x4x4 cube. So that's why it turns here. And I'm just going to move through. So it follows this pretty basic path. Nothing too interesting here. It does what it can. And then okay, so oops, sorry, I got ahead of myself. So you can see what it's doing here is it decided that it couldn't okay, sorry. So let me back up real quick. So when it got over to this other side, it split the component, right? You can see it there, and we'll go back to the first backtrack. Sorry. Okay, so it's here, and then when it moves there, it split the component, or split the antipath, so into two components. So we know that it's never going to be reached, so it goes ahead and backtracks. And it backtracks again because it didn't have the option to go straight because it had already had two straights in a row. So it goes through that process again. And so we backtrack for a while. And it picks those up. And it does as many straights as it can. Then it changes. Now at this point you can see we've got the two no exits. So as soon as that happens, well, okay, so there it could have cut back in. So as soon as it goes to that, it finds two no exits. So it has to back up. And then it says, well, I've got to pick that up. So it knew it had to pick that up, and we go through that process again. So you can see I got the no two exits, and we move through there. Got two straights and finishes it up. And at this point it would write that into a solution. Okay. Then it backs up. And it's looking for more ways to do that. Now the thing is, at this point, it should be pretty clear to us that there are no real good ways to get into that without making some big changes early on because of that long ending. But I don't have anything in the program that's doing that for me. So we'll just run through a few more. You can kind of see, you can just watch it do its work a little bit. So it really only has a couple stipulations. Clearly it can't cross a path. It can't enter something that's already in a path. It can't go out of bounds, so it has to stay in the 8x8. It can't have three straights in a row, and it can't split the component because it already knows that that would never lead to filling all of them. And it can't have two no exits. So that's how it runs through that situation. Okay. So there may be other ways to run through all the options. This is what I came up with, and so I went with it. And so it runs through quite a bit. So this, you can see there's 531 pages here. We got to the first solution pretty quick, and this just runs through. I only did this PDF is just two solutions. So it runs through all of its work until it gets to the second solution, but I won't do that now. Okay. So as that kind of catches up with me, we'll move on to look at some of the full paths in a minute. So one of the big things, one of the key mechanisms is the memory, because I had to figure out a way not to repeat the process, right? I didn't want it to just keep kind of backing up and then trying the same thing over and over. So it had to somehow take that off the plate, but I also needed it to not ignore that square altogether, because that square might be completely viable coming from a different direction. So say if I backed up a few spaces and went at a different angle, then I need those squares to be useful again. So I did that through the option list, and I'll show that more in the second video. But let's go ahead and move over to this one. So here are 200 solutions. These are all solutions, so I'm just going to kind of move through those a bit. You can see one solution here, and hopefully you saw that small change there. This just kind of runs through all solutions, and it kind of gives it an interesting feel this way, and maybe that's maybe an insight as to how I could go through the solving process in a different way. But my way worked fine for me so far. But I think this gives an interesting look at a bunch of different solutions. So these are only they're only solutions for the 8x8. There's no guarantee that these will fit on the 4x4x4, and that's okay with me, but because I do that in a later step. Now, as I'm working through this, as the path is building, it also is building a snake one step behind. So what it does is it looks at the last three pieces of the path and determines where they are relative to each other, and then it names the second to last piece. And so the snake is always one piece less than the path until the path reaches 64, and then the program knows to slap an end piece onto the snake. Okay, so there were 200, and there are more, but I'm not going to go into that. And I haven't made a PDF of all the paths that I have, but because that's not that interesting to me. Okay. So yeah. So that's basically it. So we have the kind of key component of the option list that makes sure the option list takes options out appropriately so that repetitions don't happen. And then, so to check it for a cube, it actually functions a lot like the walking through for the 8x8, except of course it uses the stuff that we saw earlier here, using the X, Y, and Z positions and using the neighbors here. But it builds the options based off of that cube, off of the snake. So if it's a 2, it only gives options that are turned from the previous 2 positions. Or if it's a 1, if the snake is a 1, then it only gives that one option of going straight. And if that option isn't available, then it backtracks. Okay. So I think I'm going to stop this one here, and then for the second video, I'll kind of talk through my code a little bit. So if you have any questions or comments, please let me know. And if you want to mess with something, or you have an idea of how to make it better, let me know.